Hi, check this out. It's a 10-watt Argon Ion Laser. I once caught a laser this big. Look at this bad boy. It's a Coherent brand, which is a US company. It's the Skylight 300C, and it dates from about 1997, and, well, they don't get much better than this. And I know what you're saying, Dave, 10 watts, that's nothing. I bought a laser cutter on AliExpress for a couple $100 that's got more power output than this. Yeah, well, yours is one of those solid state rubbish. It's not one of these beautiful ion lasers. Oh, the reason these are so good is because they are what's known as a noble gas laser, and these actually produce a incredibly coherent light source out. Hence the name. I'm here all week. Coherent. Get it? Anyway, very coherent light source that the modern ones just can't match. This one does about 470 to 514 nanometers, but you can get various filters in them and to do various things, and they're fantastic for physics research and stuff like that. So it might be only 10 watts output power, but these bad boys, I believe even still today, please correct me in the comments down below if I'm wrong, but they really can't be beat. One of these noble gas ion lasers for many exotic types of applications, but this one was actually used for outdoor laser displays, those big projection mapping laser displays, how they project laser onto the Sydney Opera House, the Sydney Harbour Bridge, and all those sort on the side of buildings and stuff like that. And this one was saved from the dumpster. Thank you very much, Daryl Tewksbury, who, here he is, here, dropping it off to the lab here. And thank you very much, because he had it in the boot of his car for like a month while I was on holidays. So thanks, Daryl. Anyway, I've done an absolutely brilliant amp hour podcast episode. Link it in down below with Daryl, and he talks about his time working at Laser Vision Australia, actually designing these laser projection systems. It's fantastic talk. So if you want to know how they actually do laser projection and those huge, massive outdoor displays, Daryl was responsible for a whole bunch of those, as well as designing a lot of the kit to do that. So yeah, fantastic talk, linked in down below. Highly recommended. So the way these things work is that they have a sealed plasma tube inside filled with the gas, and just like an old-fashioned tube, they actually have a filament in the end which you have to heat up. So it takes like a minute to start these things up, because you've got to heat up the filament. Then you apply a high voltage pulse across that to actually start up and generate the plasma. And then they've got a massive electromagnet surrounding that, which then confines the ions within the tube, and that helps increase the gain of the laser, and that's how they can get 10 watts out of this bad boy. So we'll have to leave the teardown of this for a future video. Thumbs up if you want that, subscribe, click the bell icon, all that rubbish, you know what to do. Anyway, future video. But the interesting thing about this is how you actually power it, and that's what we're going to tear down in today's video, because Daryl also saved from the dumpster not only the laser head. This doesn't have any of the power supply stuff in it. This is just the laser head itself, so he saved the power supply as well. This bad boy weighs about 42 kilos. The power supply weighs about 39 kilos. And the thing about these, they're incredibly efficient. Oh yeah, 10 watts output for around about 10 kilowatts input power. Get your confuser out, it's about 0.1% efficiency. So I don't think we're going to actually fit both of these on the bench. So let me get the power supply. So let's take this off. Oh yeah, bend the knees. And here comes the power supply. Oh no, that's got to be more than the data sheet tells you. For 39 kilos, this weighs more than the laser head. Don't want to snap my little piddly wireless microphone cable. Look at that. Look at this bad boy. And yes, it comes with an equally badass cable. Look at that. So I'm led to believe that this whole thing might actually still work, because I think it was pulled from a working environment, but it's very old, and there are issues with ion lasers as they age. So anyway, let's tear down this power supply. It's a big 3-phase jobby. So this thing has to supply up to 10 kilowatts to that laser head just to get 10 watts of light output. So where does the 9.99 kilowatts go? Well, it goes away in heat in not only here, but in the laser head itself. So that's an incredible amount of heat. You notice that it didn't have any heat sink in on that laser, really. You know, it had no big external fins or anything like that. That's because it's all water cooled. So this thing has some water pipes on the back. It's got all water cooling in it. And this, I believe, is a linear power supply, because the way those laser heads work, here's the VI response curve for it. Whilst it is fairly linear, except right at the extreme ends, it'll kind of just tail off like crazy. It's something that's actually better driven by a constant current source. So once that high voltage pulse starts up the thing, it basically kicks into constant current mode. And this is basically a water cooling unit and a giant pass transistor to basically give a linear pass transistor to give constant current, although I'm sure it's more than one transistor, and we're going to find out by opening this bad boy. So yeah, this is a piece of work. I think I'll just do the teardown on this table so it could look a bit different to where I normally do my teardowns. All right, here it is. I'm going to do this teardown in 4K for those who want to see. Hopefully we get some detail. Anyway, here's the badass plug on this thing. Look at this, 50 amp Clipsal jobby. This is a 5-pin 3-phase, although they're only using the 4 pins in there because they've got the 3-phase and the earth, and that's it. And just very briefly on the front, there's nothing doing here. Just got a laser on-off key switch, CPU okay, power supply okay. Yes, this is all CPU controlled. It's not just the pass transistor. As I said, it's got a little bit of intelligence to do some stuff. But yeah, it's basically a pass transistor. And on the back here, of course, we've got to have IEEE 4008 interface. Analog interface, it's got like, I think like a 0 to 5 volt input. You can do like modulation and stuff like that. Anyway, we've got some big ass, oh, they're broken off. Actually, those levers are broken off there. Check that out. Oh, that's gorgeous. Big ass fuse holders. Oh, look at that. What a Bobby Dazzler. 80 amp, 120 kiloamps, 500 volts. Beautiful. Then we've got some other head control stuff here. Looks like we've got a couple of electronic breakers up there, 12 amp jobbies each, and the rest of it's basically just like the water cooling. Water in, this is the water out to the laser, this is the drain, this is from the laser, and a couple of the interfaces as well. You might be wondering where the power comes from. You might think, oh, that's not, you know, that's not enough to actually come out. Well, this whole interface down here, these are actually the jacks for the interface, because here is the end of the cable right here. Look at the huge 4 pins. They're the main power pins that actually plug and go to the head unit, and then we've got some control stuff here as well. And it looks like does that plug in? That's the serial interface by the looks of it. That'll plug into the serial, so it's got serial comms over to the head. But yeah, look at that. What a beast. And then it looks like somebody's just terminated a couple of the hoses there, because I assumed that you'd break that off and they'd actually go into there to get the water in. Now it's not going to just recirculate in the head. And then the remote control, here it is here. We've actually got it, a little nice little LCD controller here. The laser emission, up and down, menu and stuff like that. So it's all controlled. That's why it needs a microprocessor in, because it can do various things. You can tune it, you can set memories, and I don't know what light does. Is that to like backlight or something? Anyway. So we've got a date code down there, December 1997, and I believe it's 97 vintage on the laser head as well. All right, so let's crack this thing open. As I said, like, there's not a lot in here. It's basically one big giant pass transistor or pass transistor array. I expect, I don't know, there could be like dozens, hundreds of pass transistors in here to get all the power and do the constant current drive. It'll have a micro, just a probably, you know, a date from the 90s, could even be a late 80s design carried over into various products. I would expect to see like a you know, a Z80 or a 6800, or even a simple micro like a 8051 or something like that perhaps. I think it's one of these Imperial Yankee bullshit, but if I can just get that. All right, let's see what we've got here. These screws were missing, so somebody's had a go at this. I'm pretty sure Daryl didn't do it. Oh, another cover. Anyway, high voltage undercover, and there's all our processory goodness on the other side. So it looks like, yeah, we might have all our power supply stuff under like this half here. Control on the top. That's all fancy pantsy. PLCC over there, we'll check that out. And then underneath all that will be all the water cooling stuff, I'd imagine. We won't go into any detail on here because it's simply not that interesting. But anyway, for the processor fanboys, we've got an 88C196 micro. So that's a little bit more than maybe I thought. So anyway, yeah, it'll have some like interface stuff, some ADC stuff, and some serial stuff, all your basic paraphernalia and stuff like that. Although, there's a large header connector up this end, and this is the front panel. So, that's, oh, it says motherboard. I guess, does that go down to this? Okay, there were just 2 screws up here for the plastic hood. And it looks like, yep, oh, we're in. Check out those bad boy caps there. So we're going to have a 3-phase rectifier in this thing. Now what's going on here, I'll put up the block diagram. I believe we'd have, this would be our cathode transformer down here. There's an enormous filter box under the bottom there. So I don't know whether our rectifiers are in there or not because I don't see them. You know, look, here's our input fuses over here. So looking over here, we've got our black, our blue, and our brown coming in. You might know that. Oh, and our green, our big earth just goes over to a massive lug over here. And of course, they go directly into the fuse holders that we saw before. And then there's gigantic, you can't really see it. I'd have to take the whole thing apart. But there's gigantic studs on the bottom side of the fuse. So this is the top side of the fuse. Power comes in here. And it goes out the bottom. There's gigantic studs there, and they go into this huge filter box all under here. The transformer's mounted on top of the filter box. So, like, the bridge rectifier has to be in there. I'm going to have to take this whole thing apart because that's, you know, rather interesting. I'm sure a lot of people would be upset if I didn't, get all this out. I mean, we're not going to use this anymore, so I'm going to take it all apart. And these are a bunch of circuit breakers that go out. This is actually, it looks like the output that goes off to the giant cable. But anyway, we've got our large capacitor bank here. Got a bleed resistor across that, of course, because you don't want that beast to stay charged up. You can tell this capacitor bank is delivering all the power. There's a huge, thick cables going off here. These are actually going directly across the magnetic coil, confinement coil, across the plasma tube in the head. So it, like, I believe, like, there's nothing else in the way. It just goes directly out there. That's why if you follow the money here, one of those cables, they've got a sleeve over there, it buggers off and it'll go down to those 4 giant pins on the bottom of the connector we saw down there. And this bad boy here, 0.5 millihenry at 80 amps. Thank you very much. This is a simple LC filter. It's just a big inductor. It's not a transformer. It's just a big ass inductor in series with the output filter cap. Nice. Turns out there is another board under this, a huge board. I can actually see down there. So I like this. Somebody's put a cable tie through 2 holes in the board here because this is a large, like, 96-way DIN connector. So, like, you can really damage the board doing that. So they put it fairly reasonably close to there. So that should aid us in pulling that board out. Isn't that brilliant? Somebody was thinking, and we didn't have to undo the jack screws on the D connectors either. But, oh, there you go. Caution, high voltage, of course. There, we're getting down to our past transistor boards. Wow, is that the only one? Guess I didn't, like, expect to see so many connections, like big 96-way DIN connectors going over. Looks like, you know, they've got like a backplane motherboard here and going over to the past, what's clearly the past transistor array, and it's called a pass bank board. There it is. So, is that the only one? Anyway, I expected it to be kind of like self-contained. I don't know why they need so much. I mean, they've got a lot of monitoring stuff. There's lots of analog actions, 741s and LM324s and a whole bunch of LM324s along there. Oh, once I get the board out, I can show you better up close. Looks like, yeah, base emitter collector. Looks like
And unfortunately, there's only like one screw in there. It looks like maybe TO3 packages, but there should be a matching screw over there. So that's interesting. And current sharing resistors, they've got little resistors on standoffs here. That's interesting. Have they done a select on test thing or something? Fascinating. Fortunately, it might be a bit of work to get all this out. Anyway, nothing on the back of that processor board. There's no bodges or anything. That's pretty impressive. Yeah, I don't see any bodges on this. Looks like they got it right. No wuckers. Because this is not high volume stuff, of course. You're not going to, like, if you make an error on these, you're not going to, like, respin the board usually. You're just going to put in some mod wires and whatnot. But yeah, all looks good. Now, of course, I don't have to worry about this being charged up at all, because not only have I got a bleed resistor across the main cap there, so I'm pretty confident I can do that without worries, because it's been in the dumpster for, yeah, I don't know, what, a decade or more? Wow, I'm not even sure how this board is going to come out. Oh. Okay, I flipped it around so we can work on this a bit better. Anyway, take a look at the chassis. It's all on the other side as well. It's got all this, you see it falling off there? All this stuff caked. I don't know what that is. It's like, it's very powdery and it just gets everywhere. Yeah, I don't know. Like, my first thought was maybe it was like some sort of salt buildup or something, like it was used in, you know, near the ocean in some sort of salt environment or something like that. But I don't know, leave it in the comments down below if you got any idea what that is, because it's caked all inside here. You can see it right up in the case at the back. It's everywhere. It's horrible stuff. Anyway, there you go. There's our board. We can go over here like this and can have a squiz around. And as I said, there's lots of analog action. There's LM324s and resistor arrays networks all the way along there. So they've got a grid arrangement for the pass trannies in this thing. We've got various test points and whatnot. And as I said, it's called a pass bank array. And you can see how we've got base emitter, and this would be the collector down here, the screw. There's no matching screw on the other side, so I'm not sure if that's a TO3 package or not, but interestingly, got another insulated wire coming out, going through a hole in the board, and that's the same for all of these channels. I thought this axial component here up on these little standoff turrets here soldered up off the board after the board's been assembled. Then I thought these were like current sharing resistors for the individual transistors, but they're not. They're actually fuses. There you go. It's got F on the silk screen there. So it looks like this, probably 1 watt jobby here is the current sharing resistor, because you need one of those for each transistor. And that's what you do, because when you're paralleling transistors like this up, you need to ensure that the power is fairly equally dissipated between the transistors. You can't just whack them in parallel because they've got different characteristics, unless they come from like physically the same die, and they're actually die matched transistors. They're not going to be well matched. So you put a little current sharing resistor in series with each transistor, and that just helps when they're in parallel to actually do that. And it looks like they've got an LM324 up here dedicated to sort of like a string of 4 pass transistors, or 4 in parallel, and then they've got like multiple groups of those. So yeah, each one of those is individually fused. You got to have that, because if you get one transistor fail short, it's going to take down the whole array and it's going to ruin your day. So they're individually fused, and having them on the turret standoffs like that, it means you can get in there and you can actually repair these things easily. Nice. So this array is not hugely high voltage. You're only talking about, 250 volts maximum up to 40 odd amps. So it's, it's the current, but it's the total power. I mean, the total, you multiply those and wow, that's a lot. But anyway, yeah, I'm not seeing how this board comes out easily. Got a bus bar happening over here. Okay, so it looks like what's happening here is we've got the bus bar, this negative here, this goes to like a metal well, it looks like huge chassis down the bottom, big black, like whole base plate kind of thing, and then it looks like we've got this bus bar going across here. It looks like it just joins 4 bars, which then looks like it probably runs this whole length of the board like this, which is what you'd expect when they're all paralleled up. So yeah, how this board comes out of here though, it's stuck under a railing at the top. You almost can't get it out unless you slide it out the front. Yeah, maybe disconnect this and then slide out the whole water cooling thing perhaps. But anyway, it's going to be interesting to see what transistors they use under here and how they're thermally coupled to the big water sink block. I can see one of the tubes going around on the top there. So how they're actually thermally coupled down to that. So, but anyway, it looks like the board can't come out. It's got to like slide out the front with this black like Delrin type railing. Warning, Will Robinson, warning. Right, so I started taking out a screw here, then I realized, no, this thing like comes out, there's 2 Phillips here, and there's a reason this puppy has a handle. So, taking out those, I don't see how the bottom can slide out without the board, so probably the whole thing is going to come out with the DIN connector. Yep, there you go. Beautiful. Oh, that's fantastic. We've got another board underneath. Check it out. Okay, let's have a quick sneaker peek under. Oh, we got some big ass resistors under there. Check those out. No, I was wrong about these resistors on the top being your emitter resistors, your current sharing resistors down here. No, they got real big beefy ones down here. So, and yeah, some TO3 transistors under there by the looks of it. All right, this is what we came here to see. Looks like there's a big plastic cover. You can see the TO3 packages under there. So it's all a little bit more discreet-y than I had in mind. Lucky last. And we'll see an array of TO3 packages and the big current sharing resistors. Ta-da! All hooked onto a bus bar. Very nice. Look at that. So yeah, that's what I was kind of expecting. I like the little ceramic standoffs down there. Check those out. That's pretty groovy. I like that. Because you don't want the whole thing flapping around in the breeze. Because this is fairly long. You can give that a wiggle, 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 yeah. Oh, okay. Those screws I took out, they were actually going into the ceramic standoffs there. Nice, but we're not talking about thousands of volts here. We're talking like, this is like 250 volt compliance voltage maximum. So, you know, not huge voltages. Yeah, so that insulated wire we saw coming through the board there goes through our current sharing resistor and goes up to the top bus bar here, and they're all just paralleled like that. But, of course, this is only one side of the argument, right? We've actually got to have another side all paralleled up, basically. So, you might be able to see down in here, we're not done with the bus bars yet. There's another bus bar going across there. Actually, it looks like it's going to connect the case of the TO3. And that's what we expect. A few Motorola fanboys, there it is, MJI 5022s, 27th week, 97 day code. Wonder what they're worth each. Anyway, we do have, yeah, the old school mica washers, thermal paste, and the resistors, of course, they also have thermal paste on the bottom of them, but you don't need the mica washers because the resistor, the case of these clad resistors, is isolated from the terminals. Now, unfortunately, to get this apart, I'm going to have to undo a screw on each and every TO3 package. Ah, bummer. Actually, on top of undoing the screws on each and every TO3, because that's what these captive studs in the PCB are for, I would also have to desolder every single one of the collector wires as well. Oh, I don't want to do that. This thing's just gorgeous to look at. Yeah, so I'm not going to do that because there's nothing on the bottom of the board that's really of interest. So as you can see, the heat transfer block is this big metal plate here, and that's just got the water elements, tubes just welded onto them. So really, like, there's nothing under that at all. So there's really nothing to see. There's no value to be gained by taking off all those transistors. Yeah, I can get the board out, but then, like, it doesn't show us anything extra. So I'm not going to do that. It's almost artistic, like, on its own right. So yeah, I'm just going to leave that as a block. So hopefully you can see how that works. The only thing extra is that there's a bus bar run in from there which actually connects all the cases together. So they're using a bus bar for that. They're not relying upon the metal of this heat transfer block to actually do that. They're specifically putting in an extra bar in there just to get lower contact resistance across all the cases. So that is very cool. What you're looking at there is basically one big ass pass transistor to regulate a constant current through this, and they simply there should be one big ass current sense resistor somewhere which measures it all, because they don't measure these are just balancing resistors. So there's got to be another huge 20-30 amp or whatever it is current shunt resistor somewhere that allows them to then measure the voltage drop across that. And I've done a video on this, how to design an electronic load. Works exactly the same way. It's just an op amp and a transistor and a current sense resistor. That's it. On second thought, what I think they're actually doing here is that because they've got an LM324 for each one, and as you've seen in my electronic load video, linked in up here if you haven't seen it, like if you have an op amp, and if you have the emitter resistor like that, you use that as the feedback, and then you can control the current. So look, they've got 4 lines coming out here like this, and they've got the resistor block. They're just series resistors going out by the looks of it to drive the base of the transistor, and then it just links over to the individual transistor like this. So what I think they're doing is I think they're actually setting constant current for each individual transistor, rather than just paralleling all the transistors and then having one external current sense resistor. And that's why they've gone to all this complexity of having all the individual op amps and all the individual control. And look, they've got some protection here by the looks of it, and they haven't otherwise this board would be like completely dumbass, and well, you wouldn't need all of this fancy pantsy stuff to drive each individual transistor. So I reckon each one is set up as its own constant current load, using that power resistor as the sense element. And then each one, of course, is individually fused. So that's how they're doing it. Just whacking a whole bunch of like adjustable current sources all in parallel. So it's not just a big ass pass transistor. So yeah, these are 2 ohm resistors. So they're actually using those as individual current sense resistors to set a constant current for each one of these transistors, and they simply parallel them all up. So then you're going to share the current across all of them. So the downside of that might mean that, well, if one of these fails, technically, then, if the fuse pops or whatever, then you're getting that amount of current less per, in your entire current going to your coil, going to your laser head. So that looks like it's probably with the trade-off they're doing. I mean, 1 or 2 of these might pop if your current changes by, a few percent. It's not going to matter much. Hang on, count these. 10, 10, 10, 9. What? I find that deeply offensive. Okay, so what that leaves us with is another board down in here with some big ass traces down there, and I don't know, is that our current sense resistor or multiple ones down there perhaps to measure that? I'm not sure. Anyway, it looks like this might be, there's our rectifier diodes. I see them. Aha, now I see the wiring flow. I don't think I have to get all this out to access to the filter. Okay, here, I think I've got this right now. We've got our 3-phase coming in here. That goes through our big ass fuses like this. And the output of those fuses goes into that giant filter block on the bottom there. That's just like a mains filter. Then the output of that comes up to these. Aha. There you go, you can maybe see Yeah, got some circuit breakers down there. So they just look like, you know, big industrial circuit breakery things, okay, like 3-phase breaker, whatever. And then the output of those comes over to our input rectifier. This is our 3-phase rectifier. I'll try and get the board out of here, show you the diodes, but basically we've got 3 big diodes here for rectification. And then the output of that, which are these 2 bad boys here, they go over by those thick cables over to our LC filter here, so through a series inductor, and then our main caps like that. And then our caps bugger off, as I said before, down to those terminals on the front down here, which then go directly over the magnetizing coil is directly in parallel with those caps. The magnetizing coil in the head, in the laser head, is directly across those caps there. All right, I've got all the screws out of here, and these go down to various blocks and components down the bottom. And once again, we've got a neat little pull cable tie here. It looks like we've got some connectors going back down to another level as well. And of course, you've noticed the big ass fan down in there. So let me tug on this. There we go. And yeah, oh, forgot a couple of screws down here. It looks like over here, they weren't relying on the PCB traces to carry all the current, which you wouldn't, of course. Yeah, there we go. There you go. That's under the board. So yeah, that runs like that. So you don't rely on, so these ones on the PCB might be handling significant current, but it comes a point where no, let's use a big, thick block like that to connect, there you go, to connect to those like that, because you just can't get that sort of low resistance on a PCB, even if you use, you know, ridiculous thicknesses of copper. It's just, yeah. So, here we go. It's gonna come out. We're out. Whoa-hey! Woohoo! Look at that. There we go. Oh, look at, wow. Look at that. Is that our current shunt resistor? 20 ohms plus minus 20%. Oh, reefer caps, reefer madness. Yeah, you probably wouldn't want to power this thing up after all these years. I've done videos on reefer madness. Got a 20 amp cartridge fuse over here. So that's interesting, because we saw our metal bar join this before. So it looks like that 20 ohm resistor is directly across there like that. Canthal. Huh, interesting. 20 ohm, 20%, like it's just like a gigantic ceramic body with like a conductive coating on the ends. That's really fascinating. I've never seen a resistor like that. Hang on, I think we have some magic smoke released. Yeah, magic smoke. There you go. Wah, 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 wah. I think there was supposed to be 3 there. I think there's one in the middle that has disintegrated. It's just completely disintegrated. It's Gonski. Oh, wow. Look at that. You know, something of this expense, you wouldn't bin it just for that. You would try and repair it, I'd imagine, but maybe it was coming to near the end of its operational life, because Laser Vision Australia, they have switched over to RGB lasers, because for their sort of outdoor applications and stuff like that, they just don't need the coherence. They just don't need the Coherent brand ion lasers. So anyway, there you go. A whole bunch of power supply stuff. Small frame, that's called the small frame power supply board. Anyway, I know you relay aficionados have probably been drooling over that thing. Wow, that's a bit of a beast. It's a Shrek, made in the Czech Republic. Hi to all my viewers in the Czech Republic. Wow, it's a bit of a beast. It's only 12 volt, it's only 10 amp, but it is 400 volts though. And I know you want to see in the rest of it. Well, let's have a look. As I said, these are some big ass diodes down here. I'll show you the side. Looks like we've got some bridge rectifiers there as well, and they I love how they just like big standoffs. They're using those as electrical standoffs to go up into the thing, and it looks like this is part of the water cooling block as well, so they had to get the heat because the inlet, this is the drain port on the back here. So this says from laser, so the water from the laser comes here, and you do have a drain port if you want to actually, is there any water in there? Any water stuck in there? No, I don't think so. And yeah, and then the outlet is over there like that. So obviously enough dissipation in the input rectifier diodes and this diode bridge here to warrant a thermal block and to get the heat out. And you might notice a tiny little thermal fuse just stuck on those. I've done those in like a very old video. I've used those on my solar sponge, my solar air heater. Yeah, it's just they open or close the contacts when it reaches a certain temperature. So it's an over temperature protection. But moving right along, down here, there you go, all this goes off to our head here, and these are the big ass cables coming in and going off to the head. But then it looks like we've got a little tap coming off here on each one, going into 3 cartridge fuses here, and then they're buggering off somewhere up to the header boards up here. So they're obviously tapping off that voltage there, but not just tapping off the voltage, they're actually extracting some power from that, because they're big ass fuses and big ass wires. So yeah. And then finally down in here we've got just like an open frame power supply that'd just be, you know, generically powering the bus over here and powering all the electronics and stuff like that. That'd be a mid-90s jobby, and that's about it. So there you go. I thought that I'd have to take apart all that, but no, it's obvious now. Oh, I forgot to show you the diodes. There you go, dual diodes, AC in, positive, negative out. Thank you very much. And we've got 3 of those. Sorry about this dodgy camera work. The other one is different. There it is. Aha, the other one there, that's not a diode, that's an SCR, or dual SCR, yeah, dual SCR. There you go. That's interesting. And yeah, they've got the control wires coming out here, and they were poking up through a hole in the board. Interesting. And yeah, these are probably just bridge rectifiers based on the configuration. So there you go. Thank you very much again, Daryl, for going to the effort to save this from the dumpster and keeping it for all that time and delivering it here so that we could have a teardown of this thing. Absolutely fantastic. And there's even bigger ones than this. This is like the runt of the litter. It's only 10 kilowatts. Like there's ones that go up to 30 kilowatts and probably even higher. And yes, I've got all the manuals for these as well, and they're very comprehensive. So they don't actually have schematics, but you know, theory of operation and all sorts of stuff in them. So I won't bore you with the details of all those, but yeah, absolutely fascinating stuff. That's just the power supply for a 10 kilowatt ion laser with 0.1% efficiency that gets 10 watts out of it. Unbelievable. There you go. Hope you found that as interesting as I did. If you did, please give it a big thumbs up. As always, discuss down below. And do yourself a favour and check out that amp hour link where Daryl and I discuss all things to do with laser vision and actually designing and implementing these sorts of systems. So, wonder how much this thing cost. If anyone knows, leave it in the comments down below. Catch you next time.